Okay, everyone, here's the rubric. Finally, we've built a lot up to this point. Gibbs free energy, equations of state, fugacity coefficients. Here's the rubric for actually doing the work to calculate vapor-liquid equilibrium. So the first question is, when you're using fugacity, what volume do you use? And how do you go through this process? So let's draw this picture. Let's draw the picture of the behavior of an equation of state on an isotherm when you expect there to be coexistence, a coexistence between phases. Recall this is the specific volume, this is the pressure, and somewhere between this point and this point there's a regime where this this isobar, for instance, P alpha, crosses this in 3 locations. For many reasons we've already discussed, this is unstable. This does not ever occur. This over here is a high volume. This is the vapor regime, and this over here is the liquid. You'll notice in the project files on the Google Collaboratory that we always plot these on a logarithmic scale. It's because this is really compressed in this region, and to make it easier to interpret and to see, we draw it in this way, but remember, this is a compressed region. Okay, so at the liquid, we'd have a fugacity coefficient that's determined at the liquid phase, and at the vapor, we'd have a fugacity, and then a fugacity coefficient calculated at the vapor phase. And so you keep moving P alpha up and down until F in the liquid phase is equal to F in the vapor phase. In principle, that's it. But the overall process, I'm going to go through it in exquisite detail. Step 1. For a given temperature and pressure, use EOS to calculate V. You have to do this using a computer. You have to use one of the nonlinear solvers in the computer to solve for the roots of the cubic equation of state. In the code that you're going to go through on the Collaboratory, the functions are already there that take care of that. So then the first thing you do is you choose which of the volumes you're going to look at. Choose the big one. This is vapor. So vapor, to choose the low density. Low density, the biggest volume you get at that value of temperature and pressure. This will be more ideal gas-like. You can use a function, for instance, like max or something like this to find the biggest value. If you run the cubic equation of state solver, you get 3 values back. You should use the maximum one. 3. Use value of V and sub into fugacity equation. Okay, for instance, I'm going to show it in fugacity coefficient form. Fugacity of the vapor phase at temperature and pressure all over the pressure is equal to 1 over RT integral V equals infinity to V under bar equals Z of the vapor phase RT over P, which you can calculate of RT over V underbar minus P dV underbar minus log ZV plus ZV minus 1. For liquid, you do the same. Okay, it's going to be exactly equivalent. So we have an L Fugacity liquid phase, temperature and pressure over pressure equals 1 over RT, integral V underbar equals infinity, up to V underbar equals ZL times RT over P. This is an L, so it doesn't look like a V, of RT over V underbar minus P dV underbar, minus log of Z in the liquid phase plus Z liquid phase minus 1. Okay. But there's a problem with the liquid one. So, problem with liquid one. For the vapor one, it's really easy. Vapor goes from V equals infinity all the way to some V. On the graph, it looks like starting out way out here and doing the integral backwards up to this point here, this first point. Okay, but for liquid, it's not so simple. For liquid, it goes through the vapor phase. It goes through vapor phase. Okay, so there's condensation. But how do we handle this phase transition? So, how to handle? How do we know what to do for this calculation of the integral? So we have RT ln FL over P equals G T P minus G IG, temperature and pressure. This is just the definition of what the fugacity is. We can expand this out to account for this transition. As we go from one region to the other, this goes from P equals 0 to P vape, V underbar minus RT over P, dP, plus RT delta, the change in fugacity from the transition, and I'll underline what these are in a second, plus vape up to the pressure that we're actually interested in, our final pressure that we need to do the calculation at, V underbar minus RT over P dP. So this first term here is the vapor form of the part of the integral. The second term is the transition, and then the last one is the liquid. Okay, the liquid phase part of the integral. Now it is time for magic. And this, I tried this on an exam before to show the derivation of a show that, and I just said it's magic. No points for you. But anyways, 2. What is RT delta log F over P? Question mark. Okay, what is this? Well, the fugacity is the same in both phases. Okay, so the change delta is equal to 0. So, delta log of F over P equals 0. Okay, this is the magic. Because it's this disappears. So we have to break this into just the two parts now. We have the middle part just disappears. This whole thing is 0. And we're going to go now from 0 to p vape, okay, v underbar minus rt over p dp. We're going to break this integral up into the two respective parts. Integral of, no, we can solve that one, sorry, we can do this first one. This is going to be equal to RT log F over P, the saturation pressure where this vaporizes. Okay. Then that's to the point of where this transition occurs. Then 2, 0, 3, integral from P vape up to P of V underbar RT over P dP equals integral P vape up to P V dP minus RT integral P vape up to P 1 over the pressure depressure. Long story short, this overall becomes the fugacity of the liquid phase, temperature and pressure, then becomes the vapor pressure times the saturation fugacity coefficient, exp 1 over RT integral P vape up to P of V underbar dP. Really, this is a small correction factor called the pointing correction. And because in real life, this graph, that we've been showing that looks like this, it's on a log scale, okay, log V. If you were to convert this to a linear scale, it looks like this. It's stretched out in a weird way. This profile on pressure V is extremely sharp, makes this is essentially a constant. The V value for this, the liquid phase density, is essentially constant. So most of the time, it's okay to just say the fugacity of the liquid phase, temperature, pressure, is approximately equal to the vapor pressure at that temperature. This is something you can look it up. You can calculate it like we've shown, and in the project you will actually calculate it for the gas that will be used. These are the steps for the overall rubric on how you solve the coexistence line and vapor-liquid equilibrium calculations using fugacity Gibbs free energy. So here we go. Let's make a block diagram for the whole algorithm. Now, not the politician, but the process. So you start by enter your parameters for your critical properties, TC, PC, omega, remember omega, the acentric factor for an equation of state, into your EOS, into your equation of state. Then you choose your temperature. Enter temperature. Then you have to choose an initial guess for the pressure, because if you have an isotherm, you have a vessel with coexistence, you don't know what pressure is inside of that. You have to guess it. That's what you're going to be iterating on. Then, of course, you compute the EOS specific parameters. compute the equation of state specific parameters, A, B, kappa, everything. Then you're going to use these Fugacity equations that are going to be provided on the collaboratory. I'm not going to go through the process of writing out the whole equation here in the notes. If you need a link to the collaboratory that's not provided, let me know. Compute these coefficients A and B. We're going to do it for the Peng-Robinson equation of state. So then A equals AP over R squared, temperature squared. B equals pressure, little b over RT. All these parameters in your Fugacity calculation and in your equation of state calculation. Okay, then solve EOS. Solve the cubic equation from before for ZL and ZV. And once you calculated ZL and ZV, you compute Fugacity of the vapor phase, and then you compute Fugacity of the liquid phase. Okay, then you do a test. Is 0.0001 greater than absolute value FL over FV minus 1. For instance, let me move this. FL over FV minus 1. So this is just an error check, test error, on is your Fugacity coefficient, is this ratio of the liquid and vapor phase Fugacities, is how close is it to 1? If it's really close to 1 within an error of 0.0001 on your computer, then you're really close to that value, and you have to make a decision from that. So here's the error testing that is done, and if the answer is yes, this error is less than this error metric 0.01, then you've achieved equilibrium and coexistence. You've found it. Coexistence. If it's not, then you have to choose a new pressure to iterate on. Choose P new equals P old times FL over FV. So you're going to adjust your new pressure guess by an adjustment of your previous pressure guess multiplied by the Fugacity ratio of liquid to vapor phase. And you will go back up to compute A, B, and the parameters for your cubic equation of state. This should take 2 or 3 iterations typically to converge on this, and you do this for each isotherm. And what you'll do when you have this all done is that you will have the calculation finished where your equation of state looks like this, except now you will have these isobars drawn on here that correspond to the actual behavior of your system, where if you're in a volume in this region, it's going to go here, it'll stay on the red line. There's going to have a flat, complete flat region where you have the coexistence of phases, the liquid phase and the vapor phase. And then it's going to continue down this line. So you'll end up with a series of solutions that will look like this. It will will look like this. Okay? All the way until you've reached a critical one, and then everything starts to look like an ideal gas. That is the long process of using thermodynamics, entropy, Gibbs free energy to figure out a simple problem of having two phases of material in coexistence.